Hey guys, so in the last lecture we have seen probability density function, that is PDF, and we have seen also one example to find the probability of reliability, that is R, and unreliability or failure rate, that is F of t. So today we are going to see a new topic, that is hazard rate. Hazard rate. So, the failure of a population of fielded products can arise from inherent design weakness, manufacturing and quality control related problems, variability due to customer usage, and the maintenance policies of the customer, and improve use or abuse of the product. So, the hazard rate, we will denote it as H of T, is the number of failures per unit time per number of non-filled products remaining at a time t. So the number of an idealized shape of hazard rate of a product is a bathtub curve. So it will be such a case. Sorry, let me draw it again. So it will be a bathtub curve. So this will be the curve. So on the x-axis there's time, that is t, and on the y-axis it is hazard rate. It is hazard rate, that is h of t. So this is h and here it is time. So suppose this is time t1 and this is time t2. So this is the infant mortality period. We can say infant mortality period, and this we can call it as wear out period. So during this period the failure rate will be maximum, because during wear out period the life of the product has reached its maximum, so the failure rate will increase. And in the starting it is just the product is just being just developed, so in that case also the failure rate will be higher. But after that a constant failure rate or useful life period, so in between that will be constant failure rate. So during usage how much products are being failure. So this will be a bathtub curve, as I said. So let's see a brief description of this three digits. So first, infant mortality period. So this product population exhibits a hazard rate that decreases during first period. Sometimes we can call it as burn in or a debugging period. So this hazard rate stabilizes at some value at time t1 when the weak products in the population have failed. So some manufacturers provide a burn-in period for their products as a means to eliminate high proportion of initial or early failures. Then this is useful life period. So the product population reaches its lowest hazard rate level and is characterized by an approximately constant hazard rate, which often referred as constant failure rate. And this period is usually considered in design phase. Then there is wear out period. So time t2 indicates the end of the useful life and start of the wear out phase. So after this point the hazard rate increases when the hazard rate becomes too high. So replacement or repair of the population of the products should be conducted, and replacement schedules are based on the recognition of this hazard rate. So these are three periods of any product. So optimizing reliability must involve the consideration of the actual life cycle periods. The actual hazard rate will be more complex in sheep and may not exhibit all of the three periods. So, what is the motivation and development? So, suppose n items are put on test. So, n is equal to number of items put on test at time t equal to 0. So, ns, so suppose ns will be the random variable denoting the number of products functioning at the time. Functioning product at that time. And n, so ns follows the binomial distribution with the parameters n and rt, where rt is the reliability of the product denoting the value of expected value of ns by ns. So we have, so I will just write expected value of ns as a ns bar. So this is expected is equal to n, the number of product put on test, into reliability of that product. So we will get ns, so the reliability will be equal to ns bar upon n. So also we have that reliability is equal to 1 minus failure rate. So failure rate is equal to 1 minus reliability. So it will be 1 minus reliability, that is n s bar upon n. So we can write as n minus ns bar upon n. And differentiating we have f of t is equal to f of t is equal to df of t by dt. So is equal to minus 1 upon n. So let me differentiate this. So this will be minus 1 upon n into d n s by dt. So 1 upon n I have taken as constant, so this will be 0 and this will be minus sign out and d ns by dt, because this is only a function of time, this is not a function of time. So only this will be get derivated. So f of t, if I, so f of t, it will be, if we write in a limit form, we can write it as limit delta t tends to 0, ns ns bar minus ns bar t plus delta t, and this is of t upon n of delta t. So because there is an n here, so this is the function of f of t. So now, so this equation tells that the failure probability density function, that is pdf, is normalized in the terms of the size of the original population. So that is n. So often more meaningful to normalize the rate with respect to the average of the units successfully functioning at time. So since this indicates the hazard rate for those surviving units, if we replace n with ns bar, we have the hazard rate or instantaneous failure rate, which is the equation. We can say that h of t is equal to same limit delta t tends to 0, ns bar of t minus ns bar of t plus delta t divided by ns bar into delta t. So you we replaced from n to ns. So this we can write it as n upon n bar s f of t, or we can write it as f of t divided by r of t. So f of t is pdf, r of t is reliability. So thus the hazard rate is the rate at which the failures occur in a certain time interval for those items that are working at the start of the interval. If n1 units are working at the beginning of time, and after the time increment delta t, n2 units are working, that is, if n1 minus n2 units fail during delta t, then the failure rate ht at time is given as h of t is equal to n1 minus n2 divided by n1 into delta t. So, in other words, uh, the hazard rate, it is rate hazard rate is equal to number of failures in a given time interval, number of failures in given time interval divided by survivors at the start of the survivors at the start of the interval into interval length. So hazard rate is thus a relative rate of failure in that it does not depend on the original sample size. So a relation for the hazard rate in terms of reliability is that h of t is equal to minus 1 upon r of t into dr by dt. So because f of t, how this come? Because as we know that f of t is dr by dt, so instead of f of t I have written this. So if I integrate the equation both the sides from 0 to t, so if I integrate both the sides from 0 to t, so what I will get, that is integration 0 to t hazard h of tau d tau is equal to minus 1 upon r into dr by uh, 1 upon r. So dt I am bringing here, this dt I will bring here. So it is 1 upon r, so 1 upon r dr will be minus ln of r, it is function of t. So if I want to find r, so what will be r? So reliability r is nothing but e raised to minus integration 0 to t h of tau d tau. So this is the function of reliability in terms of hazard rate. So some properties for the hazard rate which are valuable for understanding reliability, which we can prove also. So that is, so one property which I would like to uh, here inform, that is from time 0 to t h of tau d tau tends to infinity when time t, this time t tends to infinity. This we can prove, but there is no necessity for proof. So we know that if the time tends to infinite, the hazard rate will also increase to infinite. So that is a normal concept. So we will see an example also. uh, so before that, we'll move towards, okay, let's see an example. So there is an example. So a failure or hazard rate of a component is given by h of t is equal to, so there's curly bracket 0.015 when time t is less than equal to 200, and 0.025 when t is greater than 200. So we have to, what we have to find. So thus the hazard rate is a piecewise constant. Find an expression for reliability function of the component. So we have to find the expression for reliability function. So that is r of t. So what we know of r of t? So r of t we know that it is e raised to, that is we can write this exponential minus integration of 0 to t h of tau, this function of tau d tau. So this we know. So as it is a piecewise function, so we will also use a piecewise method. So for first 0 less than equal to t, less than greater than less than equal to 200, so that is t is less than equal to 200, and time, as t is a time function, time cannot be negative, so we are considering as a 0. So r of t will be equal to exp into, it will be minus 0 to t. So here t is 200, and 0.015 d tau. So that is 0.015 d tau. So the answer will be exp into minus 0.015, and tau will convert it into 0 to t, so it will be t. So if we are using here, if we are not using here 200, just t, so here we will just write as t. So this is our answer for first. As we have to our question is not to solve but to express the reliability function as a component, so we are not using the values here. So then for uh, t greater than 200, for t greater than 200, so what will be the reliability function? So the reliability function, we have to split into operators, two operators. So first will be, so minus, that is 0 to 200, and plus 200 to t, and here it will be 0.015, and here it will be 0.025 d tau d tau. So here there is the reliability function. So now if I've solved this, so what I will get is exp, that is exponential function, into bracket minus 0.015 into 200 plus 0.025 into t minus 0.025 into 200, 0.025 into 200. So if I solve this, what I will get is reliability function is equal to exponential of 2 minus 0.025 of t. So the four functions, that is f of t, if I write, that is f of t, small f, capital F of t, r of t, and h of t. This is hazard rate, reliability, failure rate, and PDF are all related. So if we know any one of this four function, we can develop the other three using the any equations. So what are these equations? I will just list out all the equations. That is hazard rate h of t is equal to f of t by r of t. Then r of t is equal to e raised to minus integration 0 to t h of tau d of tau. Then f of t is equal to h of t into e raised to uh, integration minus 0 to t h of tau d of tau. And q of t is equal to f of t is equal to 1 minus r of t. This is failure is equal to 1 minus reliability. So this is an example to give you a clear idea about what is going on. So we will just touch a new topic now, that is conditional reliability. Conditional reliability. So the conditional reliability function RTT1 is defined. RTT1 is defined as the probability of operating for a time interval of a duration time given that non-reparable system has operated for a time t1 prior to the beginning of the interval, and the conditional reliability can be expressed as the ratio of reliability at a time t plus t1 to the reliability at a time t1, where t1 is the age of the system at the beginning of the new test or mission. So I can write RTT T1 is equal to P T plus T1, which is greater than T and T is greater than T1. So we can write it as P is greater than T plus T1 is greater than T divided by P is greater than T is greater than T1. So R of T1 is we can write it as R of T1. R of T1 is equal to R of T plus T1 divided by R of T1. So for a product with a decreasing hazard rate, the conditional reliability will increase as the age T1 increases, and the conditional reliability will decrease for a product with an increasing hazard rate. And the conditional reliability of a product with a constant rate of a failure is independent of age. And this suggests that a product with a constant failure rate can be treated as good as new at any time. So this is the meaning of conditional reliability rate. So if we see a small example, so a reliability function of a system is assumed to be an exponential distribution such as that R of t is equal to e raised to minus lambda 0 t. So where lambda 0 is a constant, that is constant hazard rate. So calculate the reliability of a system for a mission time t given that system has already been used for 10 years. So the system has already been used for 10 years, so RTT is equal to RT plus T divided by R of 10. So this will be equal to e raised to minus lambda 0 into T plus 10 divided by e raised to minus lambda 0 of 10. So which will be equal to R of T. So that is the system reliability is as good as new reliability regardless of the age of the system. So this is the meaning of the example. So I hope you understood, and we'll see uh, in the next chapter the failure rate and other product life cycle and other things. So thank you very much.